let us discuss about the important terms that will come in a complex compound or coordination compound. We will get 6 different terms generally in a complex compound. They are nothing but central metal atom or central metal ion, ligand, coordination entity or coordination sphere, coordination number, coordination polyhedron, and oxidation number of the central metal atom and central metal ion. Let's have an example and discuss about these different terms, how we will get in a complex compound. Here I am taking a complex potassium ferrocyanide K4FeCN taken 6 times I am considering as an example. Here let us see the first term, that is the central metal atom or central metal ion. In a complex compound, generally the central metal atom or central metal ion belongs to the D block element. Generally the complex compounds are formed by the D block elements. Why only the D block elements are having the ability to form a complex compound means the D block elements are having vacant orbitals in the valency shell. The d orbital is vacant in the valency shell, either in the native state or in their most stable oxidation state. Because of the availability of the vacant d orbitals in the valency shell of the d block elements, mostly these d block elements will form the complex compound. So every complex compound is consisting of a central metal atom or central metal ion which belongs to the D block. Next, the second word is the ligand. In the next video we will discuss about in detail about the ligands, different types of the ligands and all these things we will discuss in the next video. But let us have a preliminary idea. Ligand means an atom or a molecule either charged or neutral. This may be a charged species that might have positive charge or negative charge, or a neutral molecule which is having the ability to donate the lone pair of electrons to the central metal atom is considered or called as the ligand. Ligand means an atom or molecule, either it is neutral or charged, which is having the ability to donate the lone pair of electrons to the central metal atom to make a coordinate covalent bond is called as a ligand. Here one more term let us remember, denticity. Generally we will get the term denticity while we are discussing about the ligand. Denticity means nothing but the number of lone pair of electrons donated by a ligand is called as denticity. Let us take ammonia. Here in ammonia molecule, the nitrogen atom carries a lone pair of electron. So when ammonia reacts with a central metal atom, that means a D block element, one ammonia molecule will donate one lone pair of electrons. So it is called as a monodentate ligand. In the same way, let us take Cl minus. This negative charge is donated to the central metal atom. Only one lone pair of electron or one negative charge is donated to the D block element to form a complex compound. So it is also called as a monodentate ligand. Let us take oxalate ion, COO minus and COO minus. Here you see two negative charges are present on the oxygen atom. So it donates two lone pair of electrons to the D block element. So it is called as a bidentate ligand. So friends, remember, denticity means the number of lone pair of electrons or the negative charges donated to the central metal atom to form a coordinate covalent bond is called as denticity. And the remaining features of this ligand we will discuss in the next video. So this is the ligand. Because the cyanide ion donates lone pair of electrons to the iron atom, so it is considered as a ligand, and it is the D block element which accepts the electrons from the what we can say ligand. So it is called as a central metal atom or a central metal ion. As this cyanide ion donates a lone pair of electrons or negative charge to the central metal atom, the ligands are generally considered as the Lewis bases. Ligands are generally considered as the Lewis bases. These are generally considered as Lewis bases. This term you have to remember. As the central metal atom accepting the electrons from the ligand, it is considered as a Lewis acid. Electron pair donors are called as the bases, and electron pair donors are called as the bases, acceptors are called as the acids. And the central metal atom along with the ligands carrying charge is called as the coordination entity or coordination sphere. Coordination entity or coordination sphere. That means the central metal atom along with the ligands which are represented in a square bracket is called as the coordination what we can say coordination sphere. And coordination number, generally if monodentate ligands are present, the number of ligands attached to the central metal atom is called as the coordination number. If bidentate or polydentate ligands are present, remember this formula friends, how we can calculate the coordination number means nothing but denticity into number of ligands. The formula to calculate the coordination number in a complex compound is nothing but denticity into number of ligands. Already I told you friends, denticity means the number of lone pair of electrons or negative charges donated to the central metal atom to form the coordinate covalent bond is called as denticity into number of ligands present is the formula to calculate the coordination number. Coordination polyhedron, next word we will get in the complex compounds is coordination polyhedron. Nothing but the spatial arrangement of the ligands around the central metal atom. Okay, spatial arrangement of ligands around the central metal atom or central metal ion is referred as the coordination polyhedron. Coordination polyhedron means the spatial arrangement of the ligands around the central metal atom or central metal ion is called as coordination polyhedron. Next, oxidation number of the central metal atom or central metal ion. It is very simple, you know. Oxidation number means the number of electrons that are lost by a metal during the formation of the complex compound is called as the oxidation number of the central metal atom or central metal ion. Let us have a look on these different terms, how they will be in different complexes by considering a few of the examples. Let's have a look here friends. The first complex I have considered CrNH3 taken 6 times Cl3. In this, ammonia is donating a lone pair of electrons to the chromium. So, ammonia is considered as a ligand. And here, the central metal atom will be the chromium. Chromium will be the central metal atom. Chromium along with the ammonia carrying a tri-positive charge is the coordination sphere. As the coordination sphere carries a tri-positive charge, it can be classified as a cationic complex. And see the complex here. Here ammonia donating only one lone pair of electron and 6 ammonias are there. So denticity is 1, number of ligands is 6. So the coordination number of this complex will become 6 and the shape of the ligands around the central metal ion will be octahedral. And we have to calculate the oxidation number of the chromium. We know that ammonia is a neutral ligand. Ammonia is a neutral ligand. I don't know the oxidation number of the chromium. Let it be X. And here I am having 6 ammonias and ammonia is a neutral ligand, that is 0, and total complex is having a tri-positive charge. So the charge present on the chromium will be +3. Okay friends, let's have a look here. In this complex, ammonia is donating lone pair of electrons, so it will be the ligand, and chromium is accepting the electrons, so that will be the central metal atom or a central metal ion. And the central metal atom or ion along with the ligands carrying tripositive charge will be the coordination sphere, and as it is having a tripositive charge it will be a cationic complex, and coordination number will be 6, and the coordination polyhedron, that means the shape will be octahedral, and the oxidation number of the chromium in this complex will be +3. And in the same way, let us take K4FeCN taken 6 times. Here the central metal atom will be iron, and as a cyanide ion is donating lone pair of electron, that will become the ligand, and the iron along with the cyanide ions carrying 4 negative charges, that means tetra negative charges, 4 units negative charges is the coordination sphere or coordination polyhedron. As the coordination polyhedron carrying negative charge, it will be the anionic complex, and 6 monodentate ligands are there, so coordination number is 6, and the coordination polyhedron, that means the shape will be octahedral. And here you can see iron, I don't know the oxidation state, so X, and cyanide ion is having a negative charge, so 6 cyanide ions are there, 6 into -1, and the charge present on the complex will be -4, so that's equal to X minus 6 is equal to -4, so X is equal to +2. Iron carries a +2 charge in this complex. Next, K2PtCl4. Here the central D block element will be the platinum, so it will be the central metal atom or central metal ion, and chloride ion will be the ligand, and PtCl4 carrying di-positive charge or 2 units of positive charge will be the coordination sphere. As the positive charge is there on the complex, it will be a cationic complex. As we are having 4 monodentate ligands, its coordination number is 4, and the shape of the complex will be the square planar. And the oxidation number you can calculate, X minus 4 is equal to +2. So what happens, here it is having a di-positive charge, and chlorine is having a unit negative charge, 4 are there, X minus 4 is equal to +2, therefore X is equal to what happens, +6. The oxidation number on the platinum will be +6. In the same way, K2Cn taken 4 times, the central metal atom will be nickel, and NiCO taken 4 times, the central atom will be the nickel. PtF6O2, the central atom will be the platinum. XePtF6, the central atom will be platinum. And here you just remember this, friends, XePtF6, this is called xenon hexafluoroplatinate, the first discovered zero group element compound. Xenon hexafluoroplatinate will be the first discovered zero group elements compound. Most important point, friends, definitely there is a chance to get this compound in the examination. What is the first identified compound of the zero group element? That is nothing but XePtF6, xenon hexafluoroplatinate. And these will be the central metal atoms, and these will be the ligands here, and coordination spheres, and based on the charge we are having cationic, anionic or neutral charge. You can see here in tetracarbonyl nickel the complex is having no charge, so it is a neutral complex, and coordination number is 4, tetrahedral shape. PtF6 minus is anionic complex, and coordination number will be 6, hence that is having a octahedral shape. And let us calculate the oxidation numbers in each of these complexes again. Here let us see NiCN taken 4 times. I don't know the oxidation number of the nickel, and I am having 4 cyanides, so X minus 4 is equal to +2, and again here nickel is also having a +6 oxidation state. Here nickel is having 0 oxidation state because carbon monoxide is a neutral ligand. Here you can see, I don't know the oxidation state of the platinum. In both the complexes the platinum is having the same oxidation state. X minus 6 is equal to -1, then the oxidation state on the platinum will be +5. Right, friends, this is what about the important terms what we will get in a complex compound. Right, let's have a look again. A complex compound is consisting of central metal atom, Okay, let me take another example and I will write the structure of the complex compound again and I will conclude this video. Let me take Fe. This is the central metal atom or central metal ion, and next as cyanide ion donates here what we can say lone pair of electrons, it will be the ligand, and next the charge present on the complex is neutralized by means of what we can say outside ions. So the atoms or the species which are represented outside the coordination sphere, that means out of the square bracket, are called as the counter ions. Okay, so totally here in the complex compound, what are the terms we have to remember? We have to remember number one, central metal atom or central metal ion, which belongs to the D block element and accepts the electrons from the ligands. Second one is the ligand. Ligand is the species which is having the ability to donate the lone pair of electrons or negative charge present on it to the central metal atom and having the ability to form a coordinate covalent bond, and the number of electron pairs donated by the ligands is called as the denticity. Next, third one is the coordination sphere. Coordination sphere means the central metal atom along with the ligands which is represented in a square bracket along with the charge is called as the coordination sphere. And next, coordination number. Coordination number means nothing but the number of ligands attached to the central metal atom if it is a monodentate ligand, or else the formula to calculate the coordination number is number of ligands into denticity. And the fifth one, coordination polyhedron, that means which gives the geometry of the ligands around the central metal atom, and oxidation number of the central metal atom or central metal ion, that is the number of electrons lost by the central metal atom to form a complex compound. And the charge of the coordination sphere is neutralized by means of the counter ions, right? These are the 7 different terms you have to remember while you are writing a complex compound, or the basic terms you have to remember in a complex compound. In the next video we will discuss about the ligands completely. Thank you friends. If you like this video, please like and subscribe. Please press the bell icon. Your Phanikumar, Crack Chemistry JEE. Thank you very much friends. So let us discuss about the ligands now. Ligand means the atom or the molecule which is having the tendency to donate the electron pairs to the central metal atom or central metal ion is called as ligand. Let's have a discussion on the classification of ligands. For the classification of the ligands, we have chosen 2 different parameters. Number one, denticity. Second one is the charge present on the ligand. So based on denticity, we can classify the ligands into different kinds. Let's have a look on them. The first one is the monodentate ligand. Mono means one. If a ligand donates only one electron pair to the central metal atom or central metal ion, that is called as a monodentate ligand. Second one is the polydentate ligands. Poly means more than one, many. That means if a ligand donates more than 2 or more than 2 electron pairs to the central metal atom or central metal ion, they are called as the polydentate ligands. Let us say if a ligand donates only 2 electrons to the central metal atom or central metal ion, that is called as a bidentate ligand. If it donates 3 electron pairs, that is called as a tridentate ligand. If it donates 4 electron pairs, that is called as a tetradentate ligand. 5 pentadentate, 6 hexadentate. Like that, if a ligand donates more than 1 electron pair, they can be classified into bidentate, tridentate, tetradentate, penta, hexa. Like this, these are all called as polydentate ligands. If these polydentate ligands are there, what happens means in between the central metal atom and the ligands, a ring-like structure will be formed. The formation of a ring-like structure between the ligand and the central metal ion is called as chelation, and these ligands are called as the chelating ligands. Here, if at all, here we can expect a question by giving different kinds of the complexes having monodentate and polydentate ligands based on the stability. For example, if a complex is having monodentate ligand and a polydentate ligand, so among these two, which one is more stable means the complex having a polydentate ligand. That means the complex which is involving a ring-like structure between the ligand and central metal atom is more stable than the monodentate ligands. More the number of rings, more will be the stability of the complex. For example, in a complex we are having a 5-membered ring and a 6-membered ring. Which one will be the more stable means the complex which is having a 6-membered ring will be more stable than that of the 5-membered ring. The complexes having 5-membered ring are stable due to unsaturated ligands, and the complexes having 6-membered ring are stable due to unsaturated ligands with conjugation. So that's what about the stability of the complexes based on the ligands. Now let's have a look on the next kind. The example for the polydentate ligands, you can see oxalate ion. Oxalate ion means C2O4 minus 2, COO minus, COO minus. Here it is donating 2 electron pairs, so it will be an example for the bidentate ligand. Next, EDTA minus 3, that means ethylene diamine triacetate. It's having the density either 3 or 5. If only the negative charges on the S-state ion are donated, it's having the density 3. If the lone pair of electrons present on the nitrogen atom are also donated, its density will become 5. Next, EDTA minus 4, that means ethylene diamine tetraestate ion. If only the negative charges are donated, its density will be 4, and if along with these negative charges the lone pair of electrons on the nitrogen atom are also donated, they are called as nothing but hexadentate ligand. So a ligand is having the ability to act as both tridentate and pentadentate here, tetradentate and hexadentate here. That means the density of a ligand vary from complex to the complex. Next kind of the ligand is the bridging ligand. Bridging ligand means the ligands which are having density 2. That means they can donate 2 electron pairs. They can donate 2 electron pairs to the 2 different metal atoms. They donate 2 electron pairs to 2 different metal atoms and they forms a bridge in between the 2 different metal atoms. Such a kind of ligands are called as the bridging ligands. Example for these bridging ligands are nothing but you can take N2 as an example for the bridging ligand. We can take N2 as an example for the bridging ligand, and in the same way you can take hydrogen as an example for the bridging ligand, and next you can take OH or chloride ion, or you can say take even carbonyl also as an example for the bridging ligand. Let's have a look here for the bridging ligand. Simply you can take this complex FeCO taken 9 times. FeCO taken 9 times is an example for the bridging ligand. Okay, so FeCO taken 9 times, OH, and next chloride ion can also be taken as an example for the bridging ligand. Let us take the complex Fe2CO taken 9 times. In this complex, the 2 iron atoms are joined by means of 3 carbon monoxide molecules. This carbon monoxide will donate electron pairs to both the iron atoms and forms a bridge in between these 2 iron atoms. Hence, this carbon monoxide is considered as a bridging ligand. In the same way, if we have taken another complex in which NH3 taken 5 times CO, this is cobalt, not carbon monoxide, and having the ligand OH will make a bond in between 2 cobalt atoms. CONH3 taken 5 times and the complex is it's a cationic complex having 5 chloride ions outside the complex coordination sphere. Here the OH is making bridge in between these 2 cobalt metal atoms. Hence, that is called as a bridging ligand. So, another category of the ligand is nothing but the ligand having the ability to donate two electron pairs to two different metal atoms at a time to make a bridge between them is called as a bridging ligand. Next, ambidentate ligands. Ambidentate ligands means nothing but the ligands having two donor atoms, but only one electron pair is donated at one time. It's having two donor atoms and it is having either negative charge or a lone pair of electrons or both, but even more than one electron pair can be donated by the ligand, but it donates only one electron pair to the central metal atom or central metal ion. Such a kind of ligands which are having more than one donor atom, that means either two or more than two donor atoms, and donates only one electron pair to the central metal atom is called as ambidentate ligand. Examples for the ambidentate ligands, you can take SCN minus, CN minus, NO2 minus are examples for the ambidentate ligands. And the last one, flexidentate ligands. As the name indicates, it's having more than one donor atom, but it shows variable density in different complexes. Let us take this complex here. In this complex, here what happens? Sulfate ion, in the first complex, sulfate ion density is equal to 1, that donates only one electron pair to CO. But in this complex, here sulfate ion density is 2. It donates 2 electron pairs. Like this, the ligand which is having more than one donor atom and that shows a variable density in different complexes. We know that in cobalt +3 oxidation state, the coordination number should be 6. Here what happened? In the first complex we are having 5 ammonia molecules. So 5, and here you are having 1. 5 plus 1, 6 will become the density. In this only 4 ammonia molecules are present. So the remaining 2 electron pairs are donated by means of sulfate ion. Like this, the ligands which are having a variable density in different complexes are called as the flexidentate ligands. We will see the examples at once, and then let's have a look on the second category of classification. They are nothing but based on the charge. Based on the charge, we can classify the ligands into 3 different types. They are neutral ligands, cationic ligands, and anionic ligands. While we are discussing about these ligands examples along with the density, we will discuss. First of all, let's have a look on the neutral ligands. That means the molecules which donates the electron pairs without a charge. These molecules are having no charge. The example in this video we will cover what are the different kinds of ligands based on the charge and what is their density and what is its name while we are writing IUPAC name of an organic compound. In the next video we are going to discuss about writing IUPAC names of the organic compounds. For that, it is very essential to know what is the name of a ligand while we are writing IUPAC name of an organic compound, of a coordination compound. Right, now let's have a look on the neutral ligands. Water molecule is present as a ligand. So here in water molecule, the lone pair of electrons on the oxygen atoms are donated to the central metal atom. If water molecule is present as ligand, it should be written as aqua or aquo and its density is 1. So it is an example for monodentate ligand. Next, ammonia. In the same way, the lone pair of electrons on the nitrogen atom are donated and it should be written as amine and the density is 1. That means monodentate. Next, carbon monoxide, carbonyl. It should be written as a carbonyl and it is also a monodentate. NO, it should be written as nitrosyl monodentate. CS, thiocarboxyl monodentate. NS thionitrosyl monodentate, and C5H5N pyridine, and it should be written as PY while you are writing the IUPAC name of an complex compound, and it is also an example for monodentate. Next, PH3 phosphine, that is also example for monodentate. Triphenyl phosphine monodentate, methylamine monodentate. Next, ethylene diamine, and it should be written by using the condensed letters EN. Ethylene diamine is having the denticity 2. It is a bidentate ligand. Next, diene, that means diethylene triamine. Diethylene, it is having 2 CH2 diethylene. That means CH2 taken twice, CH2 taken twice, and 2 plus 1, 3, NH2, NH, NH2. So diethylene triamine, it should be written as diene. Next, triethylene tetramine. Triethylene, that means CH2 twice groups will be 3, and we are having 4 amines, NH2, NH, NH, NH2. So it should be written as triene, and its denticity is 4. It is a tetradentate ligand. These are the examples for the neutral ligands and their denticities, and how we have to write the names of these neutral ligands in the complex compounds while writing the IUPAC name. Next, let's have a look on the cationic ligands. Here we are going to discuss or know about only 3 important cationic ligands. They are carrying positive charge over them. They are nitrosonium ion and nitronium ion and hydrazinium ion. These 3 are having the denticity 1. And next, let's have a look on the anionic ligands. That means they carries at least a unit negative charge, or more than one negative charge may be present on these ligands. If hydride ion is present, hydrido you have to write, and the denticity is 1. Oxide ion is present, you have to write oxo and monodentate. Peroxide ion, peroxo denticity 1. Perhydroxo ion, hydroxide ion, fluoro, chloro, bromo, ido, esteto, and these all having denticity 1 only. Next, cyanide ion and isocyanide ion. This cyanide ion and isocyanide ions are examples for the ambidentate ligands also. Okay, if cyanide ion is present, cyano you have to write, isocyanide ion you have to write isocyano. Both of these are monodentate ligands, and here what it can do, it can donate the negative charge present either on the nitrogen or carbon, and it can donate a lone pair of electrons present on the nitrogen or carbon. So these two, cyano and isocyanide ions, can act as both monodentate ligands, and they will come under the examples of ambidentate ligands also. Next, SO3 minus 2 sulfito, S minus 2 sulfido or thio, bisulfito ion, hydrogen sulfito ion, NH2 minus amido, NO3 minus nitrato, and NO2 minus and ONO minus. NO2 minus, if you represent in the complex, the oxygen atom will make the bond, and ONO, if you mention, nitrogen will make the bond. Both of these are examples for both ambidentate ligands, as well as NO2 minus is an example for the flexidentate ligand also, and nitride ion and azide ions. These two are also examples for the monodentate ligands. So this is what about the denticity of the ligands and the names, how we have to write the ligands while we are writing the IUPAC name of the complexes. I would like to remember you one more point again, that is nothing but here, if polydentate ligands are involved in the formation of a complex, a ring-like structure is formed. Hence, the polydentate ligands are called as chelating ligands, and the process of forming a ring-like structure with the central metal ion by the ligand is called as chelation. The complexes having ring-like structures are more stable than that of the complexes without ring-like structure. If you are having compounds having more than one ring-like structure. That means if the comparison is given between the complexes having two rings, then you must depend on the ring size. Okay, if more the number of rings are present, more will be the stability, and 6-membered ring is more stable than that of the 5-membered ring. The reason for the stability of a 6-membered ring is nothing but it is nothing but unsaturated ligand having conjugation, and the stability of the 5-membered ring is due to the saturated ligands. That points you have to remember. Let's have a look on these ligands table once, friends. If you want, you can take the screenshot and you can preserve it. Thank you, and in the next video we will discuss about the IUPAC nomenclature of the compounds. I am getting out of the frame. If you want, please take the screenshot of this board and you can preserve it for your future reference. Thank you, friends. If you like my video, please like and subscribe. The friends who are watching my channel for the first time, please like and subscribe, press the bell icon. Thank you very much. I am getting out of the frame. Please take the screenshot if you want. Thank you.